I'll let you get started. So welcome everyone. Welcome to our winter webinar with the Manitoba Grazing Clubs. Today we have with us Melissa Werkema of Future Analytics Lab in Red Deer. My name is Michael Thiele and I coordinate grazing club events, winter events like this, and summer events and winter workshops, and hopefully we'll get back to doing some of that where we can get together in person and have a nice visit as well. So the grazing club events are funded by Ducks Unlimited, and Ducks has been supporting grazing club initiatives for over 20 years, understanding the links between our stewardship of the land and the health of our ecosystems. I set up a grazing club YouTube channel. So we did do two videos with Melissa last year, soil and sap. Today we're going to try to do it all in one. So we may be a little bit over an hour, but I think it'll be a nice dense hour of discussion and good information. And so that'll be posted, and when it is, I'll send out an email so everyone knows it's up and available to rewatch. Please post your questions in the chat, and I can ask those questions as we go through the presentation. And if we do have too many questions, we'll figure that out, and I'll forward to Melissa and get a reply back to you as best as we can. So today, Melissa's going to discuss her work at Future Analytics Lab, SAP and soil testing. So great to have you back, Melissa.
Thank you. Well, there's been quite a few advancements with the soil tests. Just to give you a heads up before we jump into everything, I'm going to give you some theory beforehand, which to some may be a little boring, but then we're going to get into some calculations afterwards. So just to kind of give you a heads up, the theory all ties in with the calculations, but pretty neat things being found right now with the soil, and we're still finding things. So quite a bit different than presentations from last year, but good things. So just the first slide, we need to first start to build a foundation building a solid foundation through nutrition. And we're going to take the focus on humic and fulvic acids. The biggest things to note from here are humic acid has the abilities to form chelates with metals, along with ion exchanges with transition metals, which we'll get into. This can do so only at a pH of 6.5 or higher for humic acid. For fulvic acid, these form water-soluble complexes. So it's a difference between a chelate or a complex with organics and inorganics that are not pH dependent. So when we're working with humic acids, the pH is critical, whereas with the fulvic acids, it's not as critical. So how do I know this? I finally got this. Some of this Israeli data put together, and this is part of the work that was done at the Wiseman in Israel. So here you can see the blue line with humic acid, and it peaks at a wavelength and an absorbance at around a 6.2 or a 6. And the fulvic acid also will peak at that high point. Whereas a humic acid at a pH of 4, you start to see that's the red line right down here. And I just pointed an arrow saying it only got up to this point. How you guys are analytical like me, when it only hits this point and it doesn't peak, let's say right up to the 6, you've lost the chelating capacities. So here we can see fulvic acid peaks at no matter what pH, but a humic at a 4, which is 9, absorbance of a point. So you lost the chelating capacities at this pH. So that's how I know that. So the OSP analysis through the NMR spectra, which was of the acid and which is displayed as P. So this is each individual element that's in with humic acid. what's most important is here in this between 50 and 100 ppm range. This is most of your aliphatic carbons. And what will happen is think of on each of these peaks, there's going to be a carbon attached to each end on these peaks. So when you add nitrogen in with humic acid, the reason why you guys see such good results when nitrogen is added with humic acid is connecting only with nitrogen, which will happen. The carbons in this section will literally be kicked out and the nitrogen will be accepted as part of the entire humic molecule. So the entire unit in here. So with the steady NPK inputs with no humic or nothing organic, if the nitrogen is literally is kicking out the carbons from the humic and nitrogen is being accepted, then we decrease. So nitrogen isn't bad, but then just understand when we start to add the nitrogen in with humic, they're kicking the carbons out and just accepting as part of the entire molecule. Other point at the very beginning, chloride and fluoride, and then the remainder of the nitrogen comes out from your ammonium nitrogen, and that's this peak right in here, which is the number you'll see on the very bottom of my soil test. You'll see the root exudate ammonium nitrogen. Can you guys hear me?
Hey, Melissa. Yeah, we seem to have issues with your bandwidth. It's saying you have low bandwidth from your internet.
Okay, just give me a sec.
I turned off your video, hoping that would help.
Yeah, I'm trying to turn the video back on.
Maybe best to leave. I doubt it makes a big difference, but anything to help, because yeah, the audio was a little flaky.
Can you hear me now fine though, if we keep the audio off or the video off?
Right now you're fine, but it still was sort of intermittent. We were losing you a little bit every now and again. The odd word.
Okay, I'll keep going without the video and then
Yeah.
just chime in if I keep cutting out, and then we'll maybe figure something out.
Okay.
Okay, so with humic, it's mostly just carbons. Think of it that way, and chelate. So the humic loves the nitrogen and it will kick out those carbons and accept the nitrogen as the entire molecule. And then your ammonium nitrogen is basically just a byproduct. So just the side notes I have here, basically, and it's the nitrate, because there's two forms of your nitrogen, the nitrate nitrogen and the ammonium nitrogen. It's the N from the NO3 of your nitrate that gets accepted within the ammonium. The ammonium is so then trying to flick slides here.
We're still having some issues, Melissa.
Hey, Rebecca, can you come here for a sec? Yeah, how do I get out of? It's just completely frozen. Just give us a sec.
Okay.
Okay, I'm just going to try and stop the share and then reshare it.
Okay.
Sorry, you guys.
No problem, Melissa. Would there happen to be something else going on at the lab where you're using?
Yeah, no, we're just going to turn the Wi-Fi off on our phones because maybe that's
Okay, yeah.
causing like the more a pull.
Because otherwise, I don't see why you probably have fairly good internet coming into the lab there. Yeah.
Yeah, like it shows we have strong bars. It's just. Okay.
It looks good.
Okay, we're good for now. We just turned I think there's too many phones in here with the Wi-Fi and it just slowed it down.
Yeah, right. Exactly.
We'll try this. We'll keep the video off for now. We can maybe turn the video back on towards the end for questions, but just to keep it's going good now. We'll just keep it off.
Okay, sounds good.
Yeah, as long as you guys can hear me and I can flick the slides, I think that's important. Okay, so here's fulvic acid. So we just went through humic acid. Now this is the scan of fulvic. Again, I know the peaks mean nothing to you guys, but all it means is that one area between the 50 and 100 ppm range is mostly your amino acids and carbohydrates. And then from the left, so the aliphatic organic acids and your aromatic organic acids. These guys are your organic acids that you guys are used to hearing the names for. Let's say your acetic, citric, fumaric, tartaric, oxalic. All these guys are in with your fulvic acid. And these will favor a lower pH soil and mostly favor your fulvic. So if you guys grow a cover crop in a lower pH soil of like a 5 or a 6, you will most likely see it do better than if you were to grow that cover crop in an alkaline soil of, let's say, a 7 or 8, because the fulvics love, or because the organic acids in with fulvic acid usually typically range between a pH of 3 or 4. So when you put that in with the soil pH of around 5, it's going to love that soil pH. So you'll really see fulvic favor that. So think of humic as a chelate and mostly carbon that likes nitrogen. And then your fulvic is a lot of your organic acids that are coming from cover crops. In simple terms, just think of it that way. So then when we start to work with humic and fulvic acid, then we start to form different actions that are happening in the soil. So there's 3 main reactions that are going to occur. The first one is a carboxyl group is going to react with the metal ion to form a salt. So if any of you guys have tried to add anything with a metal, let's say if it's a humic, and then you put something in there and it seems to form a solid or like a salt-like structure, it's just forming inorganic salt at that point because you followed this reaction. The second reaction, which we're mostly after when dealing with humic, and that's why I put it in different colors. So you have a carboxyl group and one hydroxy group, which again reacts with the metal ion to form a chelate. So now if you put, let's say in farmer terms, kelp or seaweed or anything organic, which has the carboxyl group in there with zinc and a humic acid, now you formed a nitrogen zinc chelate in with that. And then the last one is if you really need an increase in your micronutrients, then you could follow that reaction. But we're mostly after this middle reaction right in here to form a chelate with your humic. So then when forming a complex with your fulvic acid, it will always favor either a metal fulvic or phosphate complex or a copper 2+ with a fulvic and your secondary ligand. Don't get worried with the term, that's chemistry secondary ligand term, but all that is, again, with your fulvic acid, is your citrate, which could be citric acid, let's say tartaric acid, your phosphate, and then a lot of your amino acids. So anything with fulvic acid is going to either follow this reaction with the copper, fulvic, and then your secondary ligand being any one of these guys down here. Or if you were to put a metal with fulvic acid and a phosphate, it's going to love either one of those reactions. So again, for soils that are neutral or weakly acidic, these will favor your mixed complexes. So at a pH of around 5 or 6, your soil is going to favor either one of these two reactions in the soil. Whereas soils that are alkaline, they're going to favor your simple complexes, which is before with your humic acid. So then when soils where there are high levels of sulfates or bicarbonates, the bicarbonates in your water, these guys are going to start replacing these secondary ligands in there. So if you have a high sulfate or bicarbonate in your water, you're going to have less effect of these guys right in here because the bicarbonates and sulfates will start to take over. And then I just made a note on the bottom, which we'll get into. You'll see an increased evidence that there's huge correlations in between the balancing of your humic and fulvic acids along with these complexes in the soil. So
hey, Melissa, maybe this is a good place to pause. I have a couple of questions here, so let's do that before we get into the sample soil report.
Sure. You can hear me okay still?
Yeah, every now and then there's still an odd loss of a word, but I think we're a little better, Could you kind of just talk through again the difference between humic acid and fulvic acid? What are the basic differences?
Yes, so humic acid, think of humic acid as just carbons. Because in here you'll see, okay, there's aliphatic carbons here. Here, these are carbons that are going to be substituted for nitrogen. These are aromatic carbons that are not substituted by anything. So you just basically get carbon out of this. You have nitrogen again, and then your carbon in your other group. So think of humic acid as just carbon that can work to form a chelate with other nutrients or work with nitrogen. Whereas fulvic acid, think of it more as if we're talking about our organic acids, like your citric, more of the amino acids, more of your carbohydrates. So fulvic is much more complex in terms of like your organic acids in your amino acids, carbohydrates, than humic is. Just think of humic as carbon.
I lost you there, that last statement.
Just think of humic acid as carbon that wants to chelate. It wants to, humic acid wants to combine at the proper pH, as long as your pH is above that 4 at least, preferably the higher the pH on a product, the better. And then that pH is going to depend on how well it's going to chelate. Because
right now, when you're talking about humic versus folic, you're talking about products that we would buy to use as an input, not the plant actually exuding these into the soil, correct?
They could be both.
Could be both. Okay, so all right.
Because humic acid could also come from your organic matter.
Right. Okay.
So the higher organic matter, yeah.
Okay, just for our context here in Manitoba, most of our soils are high 7s or 8. It's kind of normal. So we can sort of talk about that more generally as what we have to deal with here in Manitoba. There's the odd spot that may be a little more acidic, but we tend to be high 7s, low 8s.
Yeah, so there you go. So you guys are with your soil around a 7 or 8, your soils are going to want to favor humic acid. But now if you come in with a cover crop that's going to favor fulvic acid because of the organic acids in there, if I get a soil test in and I see most likely if there's been a cover crop, I'll see fulvic acid be higher than your humic acid. So at that point, now you've thrown off the balance between the humic and the fulvic acid. So to get the same result in your cover crop or your fields with a high pH compared to that with a lower pH, you would need to come in and add a good humic product to bring that balance back because your pH is higher and the fulvic is going to want to favor the lower pH. So we're constantly trying to balance that humic and fulvic acid ratio. And there's a reason for that. And if not, then you'll start to see tie-ups. So there's nothing wrong with the cover crop. It's just having to come in with humic acid to maintain that balance. Whereas in a lower soil pH, you'll see the fulvic really take off and it obviously favors a lower pH. So most of the time you'll see a cover crop do better in a lower pH soil.
Yeah, that's interesting. I haven't heard it said that way before. So what you're saying is so say we have a pH 8 soil, we do a complex, diverse, all-season cover crop. That's going to produce a lot of fulvic acids. Like those are root exudates that are being pumped into that soil. What you're saying is that we should come in with a humic foliar to help balance what?
To bring the balance.
Okay.
Yes.
All right.
With a good pH. If you don't follow that pH with the humic, then you're literally just adding carbon for no reason. That won't bring that balance back because the humic wants to form a chelate.
Right. Okay, good.
Good.
I think we can continue. There's a question here about testing different qualities of humic acids, but you'll maybe get to that.
Yeah, because that's a huge, I could do a whole presentation on different products and how they differ, but there's huge differences and it's how the companies are even extracting the humic, right, what they're doing with it after, and there's wide variances, you guys, and there's things to watch out for sure.
There is a question here that maybe we could cover now in the context. We were talking about diverse cover crops. The question is, would not a crop, so now I guess you say, like a typical monoculture crop, say wheat or canola, or an intercrop do the same as a cover crop? Can you explain this?
So on intercropping, I like intercropping because it will have the same effect as your cover crop. With a monocrop, there's less of your fulvic acid or your root exudate in with that crop. So you don't get the same effect, and that's in the seed itself. There's more of your organic acids in with the seed of a cover crop than there is with just a regular monocrop. So
that's just a function of the diversity of plants that are being grown in a cover crop versus a monoculture?
Yeah, so there are still some, you can't say that there's none, like no organic acids in with the monocrop, right, but you're not getting nearly the same amount as if you were to intercrop or have a cover crop with that.
That's interesting. So the follow-up question, what is, are all cover crops the same?
No.
Right,
No, and we're going to see some examples of, I really like fall rye. Fall rye is one of my top favorites right now. We'll get into that. It's part of this, but a lot of like your root exudates in there. So let's say fall rye has a lot of your oxalic acid in there, whereas other cover crops are going to have more malic acid. And each of those acids are going to help release most of your micronutrients. So each cover crop has different organic acids in there. So that's why the more variety that you have in there, the better to release mostly your micronutrients. But then too much, and you've offset that balance to the humic acid, and now you've tied up the system again. So in no means am I saying cover crops or intercropping is bad, but you just have to know what it's doing to create that balance again.
All right, I think we can continue.
Okay. So here's an example. So now, and there's also additions on the right-hand side for the soil test. So let's say this was your test. You're first going to see the pH of 5.2. Obviously, at that pH, it's going to favor your fulvic acid. So fulvic acid is leading down here. So we see that a 0.35. Humic acid is slightly lower. So this is preferred. So this ratio, because the fulvic is leading at the pH of 2, directly ties in with calcium. So that's why it's so important. If these ratios are very far apart and you always calculate from the fulvic to humic acid levels, if these ratios are too far apart, or the humic, let's say, was leading in this case, then you've created a calcium tie-up. And the minute we've tied up calcium, then it starts to affect all of your micronutrients down below. So you could be, so that's why it's tricky. And it's nice to know if you get a soil report back, are you low in calcium, or is it showing up low because the humic and the fulvic acid ratios are off? That's very important. So then the corresponding SAP report, here we can see, because a lot of the times in the SAP reports, I see calcium tie up, and then the micronutrients are just, they're doing the best they can to come through. But in this one, we could see the fulvic leading. And as the SAP, a lot of their micronutrients down here, silica could come up a little bit, and I could get into that too. There's a reason for that. But we see like iron, manganese, zinc, boron is coming through, copper, moly, like you start to see all of these micronutrients come through because your calcium, he could increase it a little bit. But let's say if that humic and fulvic ratio is flipped and calcium is tied up, then these guys are going to do the best they can in your SAP report to come through. And here's fall rye. This is in Saskatchewan, just straight up. So the first leaf, or number one, the light blue, is with 0 nitrogen. So just a straight up cover crop. And then number 2 was with just 30 pounds of nitrogen. And not too much different, but we could see just a straight up fall rye what it does. So there's calcium, really nice. We start to see everything down here come through really nice as well. But then playing around with that, if we start to add just 25 pounds of phos onto the same field, if we go back, the phos number down here was either 358 or 438, so really nice level there. So then we add just 25 pounds of phosphorus and we jumped right down to 288. So you guys would look at that and think, holy smokes, we're low in phosphorus. But now it's just a matter of that phosphorus is now tied up in the soil because it didn't need it. It didn't need it based on the phosphorus that just the straight up fall rye was providing. So then if we do even more, we did now 30 pounds per acre of N, which helped the micros, but then 60 pounds of nitrogen, then you can really start to see the impact. So the 30 pounds of nitrogen is the number 2. So there's these 2 arrows here compared to, let's move this right in here. So we could start to see how the nitrate started to fluctuate back and forth. But then with that nitrogen, the calcium was hit and all of your micronutrients, comparing this section down here to just this, with the increase of nitrogen, you could really see the impacts of these guys starting to be affected. So here is I can't see the top, but I believe it's a good example of a soil report with a high pH. So at an 8.3, we want to favor humic acid. So here we see humic acid being favored at the 0.18, and fulvic acid can come up. It's a little lower, but it is preferred at that pH. And we see calcium come through nicely. So there's just another correlation. So now I could start to trust most of these micronutrients coming through because this ratio is falling what the pH should be. And then just the soil to sap with another one. So here we can see at the high pH of 8.3, again, we would want to favor the humic acid given this soil pH. But here we can see fulvic. So this is what a cover crop is going to do. You're going to see a higher fulvic acid here, but then you need to increase the humic. And directly we could see the pH at 65, calcium be hit right away. And then it even correlated to the sap. So now if I get a sap report, obviously this calcium is low. I don't trust any of these guys here because calcium is tied up. So now if I don't know the soil and where you guys are at, if I see low calcium, I don't know if you can just go ahead and add calcium or if you have to correct this ratio, because it could be either one happening. But in this case, it's clear that the humic acid needs to increase the calcium, which would then tie in with the sap. And then I'd start to trust more of this bottom section down below for the micronutrients. So roles in soil fertility. This is, I could speak very slow because if you guys wanted to write notes, this is really important. The dissolution in the form of chelates has an important bearing on soil fertility, especially your micronutrient availability. Fulvic acid in concentrations at just 5 mils per liter inhibits your oxides, allowing for minerals to be accessed by plant roots. And then the third paragraph, which is most important, is many of the cations chelated, or essentially micronutrients, are made plant available by exchange. This exchange is very different from the classical CEC, or your cation exchange capacity, from any other lab. The cations present in the Adama soil test cannot be replaced, example, by which you guys are used to, your potassium, sodium, magnesium, or potassium, because these cations are not capable of occupying the position of the copper-2 ion or other transition metals in the chelate. So when we start working with humic acid, now we start to have different exchanges occurring rather than just your typical CEC that you guys are used to. So a chelated transition metal can only be exchanged by another transition metal. And now we start getting into, if you guys have heard, depending on like pH, iron starts to play with zinc, or manganese starts to play with iron, and any of that starts to occur. That's because of your humic acid in the form of chemistry being used. Because of chelation, diffusion and mass flow of micronutrients to roots are increased. Chelates provide the carrier mechanism by which depleted nutrients at the root surface become replenished. I said that chelated iron, manganese, and zinc are pH dependent and correspond to the stability of the metal. And for soil pH, the applications will depend on whether humic or fulvic acid should be applied mid-row or seed row. So how do I know this? Let's go back to the periodic table. If you ever saw this guy, it's like I could even stop on this slide because this is how we know everything. So your CEC, where you guys are used to, are just these first two sections on the periodic table. So you're used to sodium, magnesium, calcium, and potassium. That's where your CEC is coming from right now. But once we start to introduce cover crops, anything organic, your humic acid, your fulvic acid, and anything where we start to talk about chelates or complexes or anything, all these guys in the middle section in the yellow, these guys are now our cations. So that's why our cation exchange is extremely different than from industry, because you guys have been stuck in these two first rows. Now we're opening up all this. So then from the periodic table, there's an ionization energy that occurs. So your energy increases moving from left to right on the periodic table. So if we have equal ppms of both, let's say, copper and zinc, the zinc, because it has a higher energy from moving left to right, is going to be more plant available because the energy is higher than copper. So now if we start to play around with different ppm levels, let's take an iron at a ppm level of, let's say, 4 to a ppm level of zinc at 1. Because the ppm is higher on iron, it will win. But now we need to just understand what's going to exchange within this section the minute we start to introduce anything organic. So then here we go with carbon. Carbon is in another section. Carbon is your humic. So we see nitrogen be right next to carbon on the periodic table. That's why when we add nitrogen in with humic, we see some really good results because they're right next to each other on the periodic table. Also, in with carbon, same color on here. So carbon is also attached to your phosphorus and your sulfur. So with a better balance between your humic and your fulvic in your soil, and we have carbon flowing through, now we start to access phosphorus and sulfur. It's all from the periodic table. So then, if any of you know, there's a zigzag line that literally comes right down here on the periodic table. So poor boron is literally sitting right on a zigzag line. So if any of you guys have trouble with boron, is because it could literally transition from being a metal or a non-metal. So depending on the environment in the solution that you add boron to, it will literally switch from being one to the other. And silica, think of silica as being different. How silica will be, how it will act in the soil to the sap, it actually has direct correlations to calcium. So the better calcium availability we have coming through in the soil based on, again, your humic and fulvic acid ratios, then we can start to improve silica, because both calcium and silica in the plant contribute to your cell wall strength. So this is all, again, the chemistry used. You guys are used to inorganic chemistry, which deals with the synthesis and behavior of organic and organometallic compounds. And organic chemistry is now the study of the structure, composition, properties, reactions, and preparation of carbon-containing compounds. So inorganic is where industry is at, and I'm starting to bring in organic chemistry for you guys, because now we're starting to deal with carbon and the balance of everything, so the form of the chemistry is now different. Can you guys still hear me?
Yep, it's been quite good. Yep.
Okay, so inorganic strong acids. Just some notes: inorganic and organometallic compounds not only can be further developed into strong inorganic acids, so that's where your nitric, hydrochloric, sulfuric, they're also called mineral acids. That's the acids that are being used to extract your nutrients in other labs. And they can also be used to further be developed into pesticides. But remember, the Adama soil test, CEC, cannot occupy a copper 2 position, whereas the use of strong inorganic acids can. So there's a big difference there. An inorganic acid, I just said, also referred to as a mineral acid, is derived from one or more inorganic compounds. The Industrial Revolution brought on these acids, And now manufacturing plants have mastered the art of synthesizing large volumes of either the nitric, hydrochloric, sulfuric, and perchloric acid. These acids and their conjugate bases are the bases. And then I said they can even be further synthesized into other things as well. So then let's say if you got another soil test done and you're in your CEC. These CEC levels are calculated. They're not measured. Sometimes they'll measure them if there's high amounts of hydrogen, but most of the time you can calculate them and they're very close. So they do this by each element that has its own atomic weight as found on the periodic table. So if you look at a periodic table, calcium has a weight of 40, magnesium of 24, potassium of 39, sodium of 23, and hydrogen of 1. From these weights, now you can calculate their equivalent weights given the amount of valence electrons. So calcium has a +2 charge from the periodic table, which then becomes 20 as 40 divided by 2. And we could do that for each one and get their equivalent weights. So as an example, a soil test, let's say, shows 283 ppm of potassium, 265 ppm magnesium, 1140 ppm calcium, and 52 ppm sodium. What's the CEC? And your pH is 7.2. So now we just take the ppm divided by, let's say, the potassium at 39 times 100, which would be 390. And we do that for each one. You add all these guys up and you guys get a CEC of 8.86. Great. That means nothing to me from my knowledge. From this CEC, now we can calculate the percent base saturations from each one. So your potassium from up here divided by your CEC times 100, and you start to get the percent. Then they add all of these guys up to magically get 100%. You guys are like, perfect. Well, we get 100%. So let's do the same concept calculation-wise for the Adama soil test. And you guys are going to look and you're going to gasp at a 1.41 and think, holy smoke, she's wrong. She must be wrong with the CEC level of a 1.41 because we're so used to our CEC between 7 or 10 or whatever you guys want. But then, ironically, if I take that CEC and I calculate my base saturations, which are now included on the soil report, now we start to get the percents. And look at that, I can add everything up and still get 100%. But now we're taking these percents worked into the humic and fulvic ratio, and then we can start to see what's happening. So I've just given you some examples. They're working out, and I know, oh my goodness, the CEC is only a 2.38, but then we can start to see a base saturation. And usually 6 calcium at anything lower than 60% is low. So here, now if how you look at this now, if there's a humic and fulvic, this one is, they're low, but they're nice and close together. We see calcium doing really nice. And now this base saturation of basically 67%, and they've got nice calcium levels, so they don't have to worry. Here's another one. So on pH of 8.3, we want to favor the humic acid, but we could see the humic acid is lower, the fulvic acid is higher. We see a tie up in calcium, but let's calculate the base saturations, and they're below the 60%, which is lower at the 56%, so they would need calcium. So this base saturation is saying, yeah, okay, their humic and fulvic is swapped here and it is low, but now that I see the base saturation at 56%, they would definitely need to come in with humic acid and calcium. But there's also some times where this ratio could be flipped and the calcium, let's say, be at 70 or 80%. So at that point, they don't need calcium. You just need to correct this ratio between the humic and fulvic to get that calcium going. And oh my gosh, I know my CEC's at 0.59, so I must be wrong. But this ratio difference between the humic and fulvic at even a 4.5, that's getting quite high. We like to be around a 1 or a 2. Just another one. So here we could see calcium's at 35%, quite low. It's coming out really nice on the soil report here because the ratios are so good. But by the season after that, they will need more calcium because their base saturation is at 35%. And there again, just a ratio at 1.2, really good ratio. They literally used all their calcium, but they will need calcium. So then,
maybe
why that's important.
Can we stop for a second, Melissa?
Yeah.
Let's take some questions. So I think this one's appropriate when you're talking about humic. So here's the question. So practically, if humic ratio is 4.47 in the example that you had, how many liters per acre are we talking to try to correct that?
That will depend on the product.
Okay, so say
It's
you
a
had
product ppm.
Go ahead.
So let's coming down to well, you would need a really good humic above, especially a pH of 6 for this one, for it to form that chelate. And then based on the ppm level of a product that you would want to use, I have a calculation to calculate based off of the ppm that is in that product, how much you would add into that to see its effect. That's another subject too. But you can't just say, just go ahead and add this, because the plants are going to see ppm, and a lot of these products are in percent. So we need to know the ppm levels first in order for me to calculate that out to determine the rates that are needed. I won't make a recommendation unless I know what's in the product.
Right. So when a producer buys a product, is there on the label a ppm number?
Nope. They are all industry is percent, and they do have a guaranteed percent value on there. So then if you wanted to convert that guaranteed analysis from percent to ppm and trust that, that's up to the farmer, and it is fairly close. But that's listed, let's say if they had a guaranteed analysis of 10% phosphorus in that product, that would mean that they're saying there's guaranteed 100,000 ppm phosphorus in that. So even if there is that phosphorus in there, which most of the time does turn out correct, there's other levels, let's say sodium or anything that's in there that would contribute to obviously the balancing of everything. So it's really up to the farmer if they wanted to just look at that and say, Kate, I have 100,000 ppm of phosphorus, and I want you to calculate that out and determine our rate and what needs to be applied. I can do that, but there may be other things in there that would throw this balance off.
Right.
But the most important is, and we can really, like the recommendation end really gets involved in what products are being added, especially when we start to talk about your compost teas, your kelp, anything humic, fulvic, or anything in there. When I start hearing of all those different organic products out there, my first thought is, where's your soil at? Do you need the humic or do you need the fulvic? And if, let's say you need the humic, now let's narrow down what products are good, know how to use that product to get the chelating and that humic acid up, and then we have something to work with. That's the most important, aside from calculating what rate, is getting that humic and fulvic ratio correct. Because now if we have calcium coming through in the plant, now we have something to work with. But it seems here in Canada, that a lot of the micronutrients get forgotten about. Everybody's in the NPK because they know they need the nitrogen. Yes, we want potassium up front in the season for sap. We all want high potassium. But then what happens right after potassium demand decreases, right after the flowering stage, calcium kicks in. And it's literally a matter of overnight or within 2-3 days where calcium now takes the lead over potassium. And if your calcium is tied up based off of that humic and fulvic acid ratio, then everything else is going to suffer throughout the season. And that's when you start to hear a lot of these guys say we added a lot of nitrogen to get us through the season. And it seems to work, but the underlying problem is calcium.
Okay. A few other questions here. Switching gears, you mentioned fall rye. Would the other winter cereals like winter wheat or triticale be similar, or is that specific to fall rye?
That's just specific to fall rye. Triticale, I've seen a couple. I'm not a huge fan of it. I think if it's mixed in with everything, it's okay. But the winter wheat, I think I've seen a couple of those, and they're okay, but the fall rye just always seems to come out shining. And obviously, if you have a mix of the triticale and winter wheat in there and whatnot, it's going to do well because you just have more variety. But standing alone, I find right now the fall rye really, really dominates.
Okay. Good to know. Question here from Larry. He's taking a Nicole Masters course, and she's promoting using a hot water test for nitrogen to get more accurate results. What is your view on the hot water nitrogen test?
Interesting. We've actually done that. We've done both. Like we've done a hot water, like on manure, compost, and soil. We've done hot water and just regular, and we've seen barely any difference from one to the other. There might be a couple ppm difference, but it's nothing to be alarmed about and to take focus on. That's for sure.
That's good to know.
Nitrogen is nitrogen. Like nitrogen is so easy to add, and it's so easy for the plant to access that nitrogen needs to stop being the forefront of everything, but rather we need to look at the humic and fulvic ratios and where that calcium is at, especially if you're starting to work with anything organic. Let the nitrogen follow is what I think.
Yeah, get the carbon correct and nitrogen will be okay.
Yeah, and where you have to be conscious with carbon, if we just input humic acid, which is carbon, into the soil, and you don't form those reactions that occur with, because humic wants to chelate. Humic doesn't want to just be added on its own, especially in granular form, into the soil. It wants to be in liquid and have it form literally a chelated molecule to then bring those nutrients right down to the root system. So if you just input carbon or humic, most likely you'll see on my soil report, let's say on this one, you have a ppm of 126. If you just input humic, even in liquid form, which is preferred, you might see that carbon jump from 126 to maybe 200 ppm. And you guys would look at that and think, perfect, we've increased our carbon in there, so that's really good. But it's done nothing on the nutrient end to get the calcium going. What we want instead is humic being in a chelated form from the reactions that were shown, what will happen is that humic in liquid form, let's think of it just as carbon, holding the nutrients. The nutrients are brought right down to the root system, but then right when it's in the soil and near the root, let's say if that chelate had calcium or potassium as a metal in there that was holding as a chelate, that potassium or calcium now will be released into the root system to be made available to the plant, but then carbon is like a byproduct from everything. So now if carbon is a byproduct of a process that happened in the soil and we have calcium moving, we have all the micronutrients flowing the way they should, and your carbon increases, that's what we want. But you can easily add carbon and block your calcium. So at that point, you haven't done much. You've just added carbon at that point. Does that make sense?
So what you're saying is when you're using a humic to try to have it with the nutrient that you want to have chelated with it.
Yes, you want to add preferably humic in liquid form as a chelate, because it's looking right away. A good humic product is looking for something to attach to.
Right
away. Like that's why we use it. And interesting, in a higher organic matter soil, you have a better balance and higher levels of your humic and fulvic acid levels. So you think years ago when your organic matter was much higher than where if I see a 6% organic matter, I'm ecstatic. And even there, you can really see the humic and the fulvic acid levels come up and the calcium is functioning the way it should. But now that we've diminished through such high inputs of fertilizers, we've diminished that humic and fulvic acid ratio. Calcium's been hit, and now organic matter takes the hit. So now it's kind of like coming through the back door of bringing the humic and fulvic acid levels up, get the calcium moving, get the micronutrients coming through, and then guess what? The biology will follow. But now we have these companies, these biological companies coming out and saying chemistry is all bad and we just need to input the biology. By no means is biology bad, but the chemistry and the biology work together. So if the humic and fulvic is offset and calcium is tied up, that biology you might see do a little bit of an increase for you throughout the season, but it's like nitrogen at that point. You're just putting a Band-Aid solution to everything. Everything needs to work together, in other words.
Yeah, I like that. Yeah.
So chemistry isn't bad. It's the form of the chemistry that's been used that has now made you guys think that chemistry is bad. But I'm coming in with organic chemistry and you guys are used to the inorganic chemistry. And there's a huge difference. So now when we start to introduce anything organic into the system, like humic, fulvic, teas, biology even, the form of the chemistry is now different and the testing needs to follow that. That's why it's so important to know what you're working with.
Okay, that was good. That was well said. I like that. Okay, a couple other questions here sort of on that same topic. What are your thoughts on replacing synthetic N with amino acids?
Amino acids are, remember, a byproduct you can think of as part of your humic and fulvic process. So again, once we have calcium moving through the system and everything is functioning, amino acids are part of that process that you get. So if you input amino acids into the soil, of course it's good, but then if your humic and fulvic again is tied up and calcium is tied up, you're not allowing for that natural, I'm going to call it chemical process to occur that eventually will lead to the amino acids. Because if we go back to this slide and you look at fulvic acid, there is quite a large size peak in there that is both your amino acids and your carbohydrates. That's all within even your root exudates that you're getting from your cover crop. But guess what? If fulvic acid is leading and you have low levels of humic in your soil and you've tied up calcium, that amino acid and those even carbohydrates are in your soil, but they're not functioning the way they should if your humic is lower because calcium's been hit.
Okay. Question about organic matter levels on your soil test, Melissa. Tend to be lower than competitor soil tests. Why is that?
Yes, and that was my bad. I was putting the weight because I was used to a weight of organic matter, whereas labs are putting a percent in there. So I've since switched to calculating a percent of it, and that is almost double than what the weight was. So I apologize for that. I'm used to organic matter in weight, but if I redid it and you see it in percent, there would be quite a difference.
Okay, all right. What else do we have? So is the carbon, that is the byproduct that you're referring to, the carbon that is in the humic product?
Yes, yes. So when you, back to the nitrogen, what will happen is the nitrogen will, in simple terms, I'll say basically eat the carbon. So it literally becomes part of that humic molecule, and only nitrogen will do that. Whereas any other metal, let's say your potassium, or now that we're considering other cations in the periodic table, so our transition metals, let's say copper or zinc or moly or anything in there, that will form a chelate now to the humic acid. So it will help that, let's say zinc, chelated to humic. The humic will help that zinc reach the root system. Then once it reaches the root system, the zinc will be released from the humic molecule, and you're left as carbon as a byproduct, and the zinc goes into the plant. So now you're left with carbon in the soil from the humic, but only nitrogen will literally take that carbon and basically eat it and just become part of that humic molecule.
Okay. Okay, another question. Would like to know if there is a rating for the cover crop species that would quantify the amount of humic fulvic of their exudates.
I have yet. This year, I think, is going to be the year for that. I need more data on that for sure. And I'd really like to see crops that even just have one or two cover crops and what the soil did, humic and fulvic, or a multi-species. But I definitely need more data on the soil end to see the humic and fulvic and what the, either it's just one or two species in the cover crop or more. But I think that'd be fascinating to see.
Well, yeah, that adds another, I think this is new information for everyone on this call. So there's definitely going to be more questions about how to understand that and what we can do if there is some sort of imbalance between fulvic and humic, depending on the cover crop. So yeah, so further to that, another question here, humic and fulvic acid in the soil as in the soil solution, I guess, sort of exuded from, say, a cover crop versus sprayed on the crop as a foliar, which is better? if you followed that.
Yeah, obviously cover crops are going to give the best results, especially if it's a multi-species. Foliar applications are fantastic. I don't have any qualms about Fulvic being applied through the product. Again, it's just knowing the product that you're working with at that point, and as long as it's a good product. But if it's a good product and you know how it's going to react now, again, from the reactions, it will either follow the metal of Fulvic and a phosphate complex, or you're going to have a metal, a Fulvic, and then any one of your organic acids in there. So if you follow that same reaction and you make a blend on your own from a product that you bought, and you know the pH and you know what's going in, I don't think there's any harm to that. And if it's a good product, I'd say you're pretty close to what the cover crop would give.
Okay, I think I had the question wrong. Sorry. What I meant to try to say, or what the question is it better to apply the Fulvic and Humic into the soil or to apply it as a foliar?
Oh, okay, sorry.
Sorry, yeah, that was my fault.
Yeah, Humic, absolutely soil applied first thing. You could either do Humic in the fall or the spring. Again, critical on the pH. Very critical on that pH level of what you're working with in the Humic. But soil applied is best for Humic, but you can do foliar with Fulvic. If your ratios are nice and close in the soil, let's say on the previous one, and I know they were low, but let's say you had a Humic at 0.07 and a Fulvic at 0.08, you could then easily, based on the soil pH that you're working with, let's say if it's this one with a pH of 8, I would go in seed row, if you can, with Humic, and then mid row with Fulvic. So you're going in applying both, but you're maintaining that balance. Whereas if there's quite a large ratio, let's say on this one where you need more Humic than Fulvic, I would just go in seed row with Humic, with a good Humic, and then throughout the season, if you wanted to do a foliar application with Fulvic, there'd be no harm. So again, it depends on how close your ratios are, will depend on how to apply it.
So if you were to do your soil test throughout the growing season on, say, just like a typical wheat canola field, would you see potentially swings in the relationship between Humic and Fulvic?
If it's a monocrop, I'm going to say you're going to see very minimal swings, but if there's an intercrop or a cover crop in with that, I would think you will see changes throughout the season. But the neat part there, it would be at that point, the soil is just because soil to the plant always wants to reach an equilibrium state. Mm-hmm. So if, let's say, you have a nice balance of Humic and Fulvic, and you have a cover crop or an intercrop in there, it would most likely shift to a higher demand of either a Humic or Fulvic, depending on what the soil or the plant needed at that point. But if it's just in a monocrop, I think you would see less dynamics happening there for sure.
Okay. Just looking through the questions here. Best time of year to take a soil sample?
Spring or fall. I get them now and I don't see any differences, but if you really want it to be accurate, spring or fall. I know it's quite cold in Manitoba, so I don't think you could get any soil now.
Yeah, you'd need a pickaxe, I think, to get much right now. Comment here. I sure would like the carbon left in the soil, not needing to go through my sprayer nozzle. Preferred to get the plants performing to a higher level.
Mm-hmm.
and store the carbon from CO2. Yep.
Mm-hmm.
I think that's a good comment.
Mm-hmm.
Is the effect of a diverse cover crop on humic and fulvic acid levels in 2021 enough to last through a grain crop 2022? It's a good question. So say you had a diverse full season cover crop.
Yeah, from what I've seen in crops that have had cover crops in there for a while, the fulvic acid really seems to hold its quality quite well. Humic seems to be used up quicker, but fulvic acid really holds on. And that's, I think, another benefit to the cover crop or intercropping, is it really holds on to its value. And but that would also depend on the organic matter content as well. I believe it hold more of your humic acid in there as well.
So would you have any general recommendations? So say you had a situation where last year you had a full season cover and it was grazed, just as an example, and now this year it's going back into wheat or canola. Any recommendations on what you would look to do without maybe a soil test? Just to,
yeah, I was going to say, just as long as I see that humic and fulvic ratio,
yeah.
I would think with grazing, you're going to get a better balance of that humic and fulvic, and then you're basically starting off the season really well with a nice ratio. But there again, I need to see the soil to know anything.
Yeah. Right. Heard you refer to a good humic product. Could you please give your opinion on what is a good product, understanding that there's different extraction methods, your thoughts? So sort of general things like pH, maybe go over all that again.
So what we do here, there's two different types of tests you can have on a humic product. They both work together. The first one is we'll measure the carbon bond strength in there. So if we have, let's say, a product come in at a pH of 9 or a 10, I'm going to start to break that pH to see the dynamics with the carbon that happens at each pH level. And that's the same measurement concept-wise that we did at the Wiseman in Israel. So if I have a product, let's say at a pH of 10, and we get an absorbance of, let's say, 5.6 or 5.7, obviously that pH of 10, you're going to have good chelating capacities. But then if I break that pH to a pH of 9, and that absorbance now drops to a 1 or a 2, now you've lost chelating capacities from a pH of 10 to 9. So it's nice to know whatever product you're working with at what pH you lose that chelating capacity. But then what industry has done, and it took me a little while to figure it out, on some products, if we start at, let's say, a same pH of a 10, it takes quite a bit to drop that pH to, let's say, a 9. But once it's broken. Like it will literally go from an absorbance of 5 or 6 to 0. Like it's completely gone from just one pH drop. And most of the time what's happening there is there has been a lot of additions into a humic product. So let's say you see a product marketed as a humic product plus iron, manganese, zinc, calcium, or calcium is out of there, but a lot of your micronutrients, that's what's happening in some of these products, not all of them, but some. So it's creating like a fake bond. So once you break the pH, it's gone. So there, it's the source of the carbon that they're sourcing it from, which a lot is from the Sheerness mine here in Alberta. But then their extraction procedure, each company can decide on whether they're going to use an acid extraction or an alkaline extraction. So depending on which form of the extraction they've decided to take as a company, that will have a huge bearing on the carbon and the chelating capacities. So now if they've noticed it's not that good, then they'll go in and add a lot of these micronutrients in there to try and make it better. But the source and the type of extraction that was used, that's what I'm after. So I'll do first the carbon bond to see the chelating capacities in there, plus the nutrient end to see, okay, if it broke at what pH, and it seems to be doing quite well, then I'll run the nutritional end plus your human. There's lignin in there because lignin will have a huge bearing on those carbon bonds. Fulvic acid and humic acid, I'll calculate and measure all of that in addition to the nutritional analysis. So you're kind of getting the carbon bond end to see the chelated aspect plus all of the nutritional ends with your humic, humin, and fulvic.
Okay. So if you're a producer looking to buy a product, is the source, it's a good place to start, the source of that product and the extraction method used? Is
Yes.
that
Yes. So if I see a good humic, what will happen is the pH is nice and high, and the best I've seen is a pH of about a 12 on a humic product, and that a product on that specific one broke at a pH of 7. So they could go from, let's say now if you got that humic product starting at a pH of 12 and you added whatever nutritional source you wanted in there at a pH of 9, even though there's a difference between a 9 and a 12 pH, it loses its chelating capacities at a pH of 7. So you would still be okay. But now if you have a pH product of 9 and it completely breaks at a pH of 8, guess what's going to happen if you're using that humic at a pH of 9 and you add, let's say, nitrogen even at a pH of 6. It's going to average between a pH of 7 or 8. So you've lost that chelating capacity. So that pH to the carbon bond strength and to see now in a good humic product at a nice high pH, let's say it breaks at 7 and they're very low in the micronutrients, that's a fantastic product to use.
Okay.
Because that's a true carbon bonded product that will chelate to whatever you want. That's what you don't want to use humic and a product for nutrition. You want your humic product to be used as a chelator.
right? I know you're just testing some of these products, but have you seen any product or brand change over time? In other words, there may be some variability, even the same company with the source of the product. So how do you deal with that variability over time?
Yeah, I don't know, but I could get one product name through one company and get the exact same name to the humic product through a different source, and the data is completely different. So I have no control over that, obviously, but goes to show you guys are working with. So you could hear one name and think it's fantastic, and then another company takes hold of it and it's now completely different than the first one. So that's industry.
Yeah, right. Question, here's a scenario. 3 years of cover crop on a field that has organic matter level of 7 or higher. What would you say in general about that and going forward now after 3 years of cover crop and grazing?
What's your soil pH?
To be around 8.
So I bet you the fulvic from there with 3 years of cover crop is very nice level, but it would be interesting to see the humic level. So if you've seen some differences year after year, I don't know, I haven't seen the crop, but my bet would be the first year would have been the best, second year average, and then the third year may have been a little less, because the fulvic is good, but then to make it better, you would need to come in with Humic.
Interesting.
Would be my guess. I don't know.
I know the field that it's Scott Duguid, and yeah, the thing that complicates that, of course, is last summer would be year 3, and it was extremely dry, so it's hard to sort of tease out whether it's just the fact that dry conditions or something else, but that's interesting.
Yeah.
Okay, I think that's it. We've caught up with questions.
Awesome. Oh, so then here's just more examples, and then it's kind of nice. So plants are going to absorb nutrients in the form of ions. So if you remember the periodic table, each one of these nutrients is going to have a different charge to them. So now if we start to think of it in sap terms, your 4 mobile nutrients being your magnesium, potassium, phosphorus, and nitrogen. These all have their separate charges. So magnesium as a 2+, potassium as +1, phosphorus is -3, nitrate is -1, and ammonium is +1. Your 7 medium immobile nutrients being sulfur, copper can have 2 charges, iron can have 2 separate ones, manganese can have 2 separate ones of a +2, +3, zinc mostly just a +2, moly can be a +3 or 6, and silica, all the variations of silica can have +4, +2, or a -4. And then boron and calcium has those 2. So the plant is going to see the charges or the ions of each one of these. These elements, when we measure products, are measured in ppm. So after an analysis of a product, this is giving us the ppm level of each element on the periodic table. This analysis in ppm can then be calculated into base saturations to determine which form of nutrient is being applied. Plants will see the ppm levels, not percent or weight. So again, the charge talked about, if you were to look, there's, if you guys have your periodic table, which I encourage you to print off on your own, zinc right here, this +2 charge, that's the charge on the ion. Copper, here's another +2 charge. Nickel, you guys want to start talking about nickel. There we go. Now, nickel is going to be part of our cation when working with humic acid. Cobalt, we could throw it in there. And there's iron. So all these guys, all these charges right up in here are all the different charges that we're now playing with in iron. There's manganese. So each one of these guys, so magnesium, there's your +2, sodium is +1, so they all have their charges there. So if our transition metals, which this whole yellow section in here on the periodic table are our transition metals. So if we're working with humic and our transition metals are now cations, that's what we could start to do when introducing anything organic into the system. We could follow the exact same concept as we did before with your potassium, magnesium, so these first 2 categories for CEC. Now we can start calculating our base saturations for all of our micronutrients. So depending on the form that you have going into your soil, which I'm sure you guys have heard, the forms are very important. If we start to see and calculate, and oh my gosh, I know my CEC is just so drastically low, so I must be wrong. But let's just keep on going here. So let's say the percents here matter. We want these percents of your micronutrients to be within certain percentages, just as we want the other 4 to be. So first rule is the manganese and iron ratio. We always want iron to be higher than manganese. And in this case, it's flipped. So manganese at this point at 53% is highly dominating this soil at an iron at 43%. But that is using different charges. So now if we start to play with the different charges that each element can have, we could start to see, based off the percent base saturations, the impacts that it will have in your soil. So if we just play with charges here, if we swap I can't read the very top, but I'm pretty sure I was playing with manganese at this point. We have manganese at 53% here. We changed the charge or the form of the product being used, and all of a sudden manganese comes down and iron dominates, which is what we want at a ratio of less than 1 between the manganese and iron. So the form of the product, huge difference in what you're using. And sorry, I can't read the top there unless I can hide the very top. I think I was playing with iron.
Yeah, it says now let's play with iron +3 charge.
There we go. So then this one must have been an iron at 2+, so iron at 3+, and we could see iron go from 52% here to iron at 43%, and manganese is again leading. So we don't want manganese leading iron, but knowing the form of what's going in, the plants are going to see the charges of what's going into each. And look at that, I can do the base saturations, and ironically, I still get 100% on my calculations. Playing with charges again. So now whatever the charge went from iron, now we have a 43%, manganese is at 53, playing with it again, and look at that. Now we have iron only at 33% and manganese at 62, which is literally dominating in that soil. So now in this case, what would happen, even if you had the calcium coming through, so here's a good cover crop situation where you have a lower pH, it's favoring the fulvic, perfect. Humic is lower, that's okay. Calcium is coming through. But now, second point on the test, once we have calcium coming through, now we have to watch out with the charges of all our micronutrients if you're applying any. Because in some cases, or all, if you're not watching the charge, now if we calculate the base saturation to the charge of the micronutrient went in, we know what's dominating. So we want to make sure we're balancing these micronutrients so one doesn't dominate over the other.
Well, Melissa, what you're saying is you need to know the form of the micronutrient when you are putting it together as a potential foliar product. Is that what?
Yes.
Yeah. So you're not referring to any particular product here, just
No.
sort of scenarios. Yeah. Okay.
I'm just showing you the forms and how it has an impact on once you have calcium moving. If you now put whatever the charge of manganese or iron was in this example, I'm just showing whatever the charge is that you're working with, how it's going to impact the overall soil for uptake.
Yep.
Here's another one. Manganese takes even more. Playing with iron again. So we always want to, like in no matter what case, this one, manganese was always higher. You can even see it high on the soil. So, okay, yeah, you have a nice ratio between the humic and fulvic. Calcium is coming out really nice. Now, this high manganese is legitimately telling me, because this ratio is so nice close together at that pH with that calcium coming through nice, this manganese is like, yeah, watch me go, because because the calcium is coming through, which helps the micronutrients, manganese is literally dominated. But now, if this ratio was offset again and calcium was tied up, now this manganese might even show low. So it's now again, and that just ties in with having to make sure this ratio is correct to the calcium, and these are true legitimate numbers now coming through. And it even shows in the base saturation at 84%. Like that's just, it's telling you you've got a lot of manganese and just something to work with for sure. Playing with charges even in an alkaline soil. So there we go. Again, with this soil of 7.88, humic ratio there, calcium is coming through. I think that's the same one, but just different charges. So I'm hoping to show you guys that the soil texture is one thing in there and it's important, but what's even more important is no matter what the texture of your soil is, the forefront and what's most important is getting that humic and fulvic ratio to get your calcium moving, and then we can start to deal with everything else. And then we just, I kept SAP short because hopefully it's easy to you now from seeing where the soil sits at to get that ratio correct. And then once calcium is coming through, now we could start to see that reflect in the SAP. So if we have the calcium coming through in SAP, then it's makes my job better and your job better. So then Sap analysis, just briefly. So Sap analysis has been researched by scientists since the early 1920s. Research began with the emphasis on the absorption of ions, which we just covered, by different plants, which to the current day has led to fine-tuning methods, which encapsulates the reactions taking place in the xylem sap of the plant leaves. Significant research, thanks to the Israelis, has also been accomplished with phloem sap. Root pressure generated in the roots plays a role in the flow of the xylem sap in the plant. And when comparing sap to tissue, again, it is the form of the chemistry being used. So sap is reduced, tissue is oxidized. So here is a simple what's happening now that I've explained your ions and the exchange of the ions in the soil. This is also happening in sap. So this is reduced chemistry. Oxidation is a term in chemistry, which means there has been a loss of electrons, and reduction is where there is a gain of electrons in an ion or atom, which is being shown with the sodium fluoride here. In terms of plant nutrients, those metals more willing to donate their electrons, which is from the periodic table, tend to have higher values after strong acid extractions because no ionic reactions are capable of taking place. It's just one entire molecule, so you get the total form of nutrients. This is oxidization. The total form of nutrients also involves complexities, which as an entire unit are not readily plant available. This is due to all enzyme activity ceasing. Through reduction, we are always keeping the electrons or charges attached to a molecule, so more clear representations of nutrients and their interactions are revealed. So through reduced chemistry, you get the available forms of nutrients. This is where the benefit of the new and the old leaf come in. By seeing the nutrients in their current state, it allows for adjustments for growth and development. So strong acid and the tissue versus the Adama soil test in plant sap. When using strong acids, inorganic acids, including sulfuric, hydrochloric, and nitric, are used as methods of extraction because plants see nutrients in different ways than what a strong acid extracts. Certain levels may appear higher or lower than what they actually are. Caution must be taken, as what I believe to be happening, as I see more, is now iron oxides are being forgotten about, which could lead to higher diseases. Oxides are the result of steady NPK fertilizer inputs with no resulting ionic balance. These oxides will then eventually begin to block micronutrients, which is reflected in a SAP analysis. Tissue analysis involves drying, then extracting nutrients with strong acids. This form gives you the total amount of nutrients the plant has taken up until that moment. These nutrients are mainly complex in the cell walls. These complex nutrients are not totally available for plant development at that moment. By allowing the oxides to appear through the Adama soil test, it provides further indications on where improvements need to be made. SAP analysis then reveals a true story on the overall health and plant nutrient uptake. Just some information if there are people in here that haven't sampled for SAP, how to collect. These are just a few examples of the new and the old. The most difficult seems to be the one with the flag leaf, so your barley, oats, wheat. You can just start to collect the young leaves. The minute there's usually if there's a leaf right in the middle here, you can then take one from the top, one from the bottom, as long as there's one, and you could follow that same concept throughout the entire season. For levels to collect, there's some good examples on the amounts that are nice to see. Makes our job easier. The mobilities, which I touched on this before, which is still the same. So your mobile being your nitrogen, potassium, phosphorus, magnesium. Medium is the middle section, and your immobiles is calcium and boron. So we're going to want to see coming into this season again, high levels of potassium as the forefront. It's going to use potassium the most before calcium kicks in. And what's happening is it's pulling the reserves from the old leaf up to the new for your mobile nutrients. And then there's potassium and calcium again. So throughout the fruiting stage, potassium is going to be the highest. To maintain this demand, the plant's going to use the reserves from the old leaves to give up to the new. But then shortly after the potassium demand decreases, the calcium availability plays a critical role in keeping the plant functioning by allowing the micronutrients to become more available. Zippers, if you guys have ever seen these zippers on the edge of your corn leaves, this is a calcium problem. So guess what? There it ties in with your soil and the humic and fulvic ratios again. If calcium is tied up, which obviously we could see wide differences here between calcium and boron. It's a combination of both calcium and boron in the case of these zippers. So correcting that humic and fulvic in the soil and getting that calcium going will help you with cases like this. And sugars. Sugars will now be included in with your SAP report this year. Sugars are an indication on your overall plant health and photosynthesis. It's going to be directly related to your nitrate levels. Thanks to the greenhouses who I test for, they could play around with these. So there's a direct correlation between the nitrate and your total sugars. So a simple approach is going to be a low nitrate is equal to a high sugar, and your high nitrate levels are going to give you low sugars. And this is mostly due to the high levels of water that a plant takes up during the uptake, which dilutes your sugars. So with obviously a high nitrogen inputs, you're going to see the nitrate. Let's say if it were up here, you're most likely going to see the total sugars be quite low. But then the lower the nitrate, then your sugars start to be impacted. So obviously a balancing of your nitrogen plays a critical role in your total sugar levels coming up this season. And that's it.
Thanks, Melissa. That was excellent. There's a lot there to try to take in. That's interesting what you were saying about low nitrate, high sugar, high nitrate, low sugar. So are you saying that this is maybe something I've heard others say, when you have a high nitrate, you probably have like a bloated cell then, because that plant is having to take in more water?
Mm-hmm. So when a plant, obviously, even in the fruiting stage right up before then, you still need nitrogen throughout that process. But as it's taking up that nitrate, the nitrate comes up with water and it dilutes in that plant, which then dilutes the sugars.
Because most of that nitrate is simply coming through, the uptake through soil solution.
Soil or the plant, yeah. So obviously you could see with high nitrogen inputs what effect you're going to have on your sugars.
Right. Question about soil biology. Doesn't soil biology buffer soil chemistry? What's that relationship? Yeah.
Yes. So you need both chemistry and biology in with everything. But the neat thing, once you have the calcium coming through, you have nice humic and fulvic, and you have the soil functioning the way it should. Now the biology comes in, and the minute the biology with that chemistry start playing together, that's when you see incredible things happen. And there's obviously, when you start to introduce the biology into the system, it kind of gets out of our control of what happens. You can run an analysis and see the biology in there. You can know what you're adding, but how it's going to interact with a balanced soil is kind of out of our control. And it's always in a good way how those interactions take place. But I come from the standpoint on get the chemistry and the humic and fulvic in line first, and then watch what will happen. And it's pretty exciting stuff.
So what you're saying is, given the current state of our soils with our management practices over, say, the past 50 years, we need to do some chemistry work up front, perhaps, to get some of that biology back functioning.
Yes, and through organic chemistry, through the use of your humic fulvic, get the calcium going. Because how many biological companies were there just 20 years ago on the market?
Probably zero.
So now chemistry's been tainted as this bad guy because it's the inorganic chemistry that's been used. So now we have these biological companies and saying, yeah, hey, chemistry, look what it's done. It's literally ran us into the ditch here. So we must need biology to get us back into where we were just 20 or even 30 years ago. But the problem still lies on the chemistry end because it's the forms that have been being used. And I didn't do this soil test 20, 30 years ago, but my bet would be if I did, the organic matter would be much higher in the soil, and there'd be much higher levels of both the humic and the fulvic in a good balance, and that calcium was moving. But now, and then with that would have been the biology that was just working together with the chemistry. But now we've depleted those humic and fulvic ratios. Calcium is now tied up or just completely used up. So yeah, biology is good, but it's not going to fix anything. It's a Band-Aid solution.
As a potential product applied to attempt to fix a problem.
Yeah, like biology by no means is bad, and it works together with the chemistry. But if your chemistry is offset in the soil and you go and apply biology, you might see a little bit of an increase, but it won't fix your problem.
Okay, that's good information. Okay, well, we're getting close to the end here today. Any other questions? Maybe this is the chance, if you have a question and you'd like to ask it directly, you could unmute and ask your question.
I turned my camera on, but I'm scared of losing you guys.
Yeah, because I think we've done okay. We got through those early problems, and it's been not bad.
I can try my camera if it helps you guys.
Yeah, go ahead.
Hey, I just hope I don't lose you.
And I will record this. I am recording it, and it will be posted on the Manitoba Grazing Club's YouTube channel.
Okay, it just says that you cannot show your video because the host has stopped it. So,
oh, that's me. Sorry.
Yeah.
There you go.
There we go. Now you can see me again. It's
There,
always
you're
nice
back.
seeing a person to talk to.
Anybody with a question in the chat or unmute? Otherwise, we'll wrap things up. Well, thanks, Melissa. I think we'll
You're welcome.
we'll leave it there then, and appreciate this. You've given us a lot to think about, so I think you'll have a few phone calls over the next the next
Wait till
few weeks.
next year.
Yeah.
We're just starting.
Yeah, exactly. We're learning more every year. So yes, we appreciate your hard work.
Thank you. Be safe, everyone.
Yeah.
And stay warm today.
All right. Thanks.
We'll
Bye.
talk soon. Okay.
Yep. Bye.
Bye.